So let's move on then to what's called the Central Limit Theorem, which is on page 78. The good news is it's the same thing we've been doing. If I asked everybody to tell me the last number of their student ID number, if I did, do you think there's any number that's more likely than the other ones? Like, are there going to be more zeros than fours? Or sevens are going to be more likely? People are all shaking their heads no. All the numbers are equally likely, right? Whether you have a 0 on the end, or a 1, or a 7, or a 9, all of those are the same. We all agree with that? That'd be a uniform distribution. Uniform, we expect them all to be the same. So if we had done that, if I asked you for all your numbers, we would have had a uniform distribution, straight across. But if I asked you to say, take the average of all your digits, so you have some numbers 0 through 9, you have an 8-digit. We could do phone numbers if you don't remember your student ID number, whatever. If you took the average, do you think you'd get very many zeros? The average of all your digits? It'd be hard to get 0. How would you get an average of 0?
None.
What did you say?
None of them have that number.
Well, actually, they would all have 0, right? The only way your average would be 0 is if your student ID number was this. If that was your student ID number, you added up all the digits and took the average number would be 0. Where if your student ID number is this, if you added up each of those numbers and divided by 7, the average wouldn't be 0. It'd be something else. Would everyone agree that average being 0 would be hard to do? How about an average of 9? If I say the average digit is a 9, how would that have to happen? What would your ID number look like if the average number was a 9? All 9s, right? If that was your student ID number, then your average would be 9. Do we agree that most of us have something somewhere in between 0 and 9, but not that close to 0 or 9? What do you think the average would be? What do you expect it to be? A lot of 5s, maybe? The average, if you added all your numbers, I think the average number would be a 5.
Like a 4.5.
Or maybe a 4.5. It's actually 4.5. Why is it 4.5? Halfway between 0 and 9, right? You would expect it to be halfway in between. So the central limit theorem says that even if you have a distribution that's not normal, the mean turns out to be the same regardless when you start taking averages. So if I took, let's just make up a student ID number. I don't want to pick anybody's because then we're all going to go check out their grades and who knows what else. So there's somebody that has a student ID number of 0081346. This particular person. If I find the mean of their digits, of this person's digits, if I add up their digits and divide by the fact that there's 7 digits there, this is what I'm talking about. If we did that, let's see what it comes up to be. 9, 12. 3 point something. Can someone help me out there?
3.14.
3.14. Oh, I just did was 3. Get a calculator. So the mean for this person is 3.14. If I did it for a bunch of people, the more people I did, do we agree that it would be closer and closer to 4.5 just because some numbers are close to 0, some numbers are close to 9, but on average they're all around 4.5. Somewhere halfway in between. That's the central limit theorem. And go back to my example. If we just looked at the last digit, we wouldn't be surprised to have numbers all the way out to 0 and all the way out to 9. But for averages, we would be really surprised if someone said, hey, the average of all of mine is 0. Because the only way you could do it would have been this. Or maybe you had 0.0001 and it rounded to 0. So what happens is your numbers get closer and closer to the middle. They get closer and closer to the middle, and they actually end up acting like they're normal. What happens though is your standard deviation changes when you take a mean. When you look at a mean or an average, standard deviation changes. Let's talk about what I mean down there, the central limit theorem down at the bottom of the page. If you have any distribution with a mean and standard deviation like we've been talking about, and your sample size is big enough, greater than 30, which is why I made you do 40 for your projects, then the sample means have a distribution that can be approximated by normal. That's good for us because we've been doing normal. With the same mean and this new standard deviation, sigma over the square root of n. What I call the new standard deviation. Your book will call it this, sigma with a little x bar down here. Sigma with an x bar, meaning it's the standard deviation for the mean. So let me give you another example of why that's different. If I took everybody in the city of Brentwood, I probably could find somebody who had a salary of, I don't know, $200 an hour. There's probably somebody in Brentwood that has a salary of $200 an hour. We agree with that? Somebody, we could probably find somebody, maybe we'd like to know them. But we could probably find somebody. But if I said, hey, the average salary in Brentwood is $200 an hour? The average? She's over here shaking her head on. No, it's not. Have you seen my job? The average is so different than one person, right? We could find one person, but to find an average would be really unlikely. So when you start talking about averages, we expect it to be smaller and smaller, less standard deviation, closer to the middle. It might be okay to find one person on an extreme end, but to find an average on an extreme, it doesn't happen. The numbers all get closer and closer together. So down there, that's where the sigma over square root of n comes from. It still works if your sample size is small, if you already have a normal distribution. Otherwise, it's not going to apply in example 3. I will never ask you to find a probability where you cannot apply the central limit theorem. There's a couple questions where it says can you or can't you, and then you just stop. But on an exam, if I ask you to find a probability, the normal distribution will apply. So not to worry that you have to figure out what do I do if it doesn't. Okay, so let's look at the subtle difference here. Example 5, on top of page 79. Now we're worried about length of pregnancies. Pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. The first question is technically a review of what we've been doing. One pregnant woman is randomly selected. Find the probability that her length of pregnancy is less than 260 days. How would I answer that question? I claim that's what we were just doing in the last section.
Draw a picture.
Draw a picture, thank you.
Where?
Draw a picture. Example 5A, I'm drawing the picture. What am I putting where? 268 is the mean. And then I am doing what? Adding and subtracting 15? 283? 298? Well, I'm adding in my head and borrowing and carrying. 313, is that right?
Yes.
Wait, I have to subtract though, it gets harder. 253? 238? 223?
Three.
She put 236 in the second
Oh, see how talented I am? I can say one thing and write another. Here we go. So I labeled my picture, and the question says, find the probability that her length of pregnancy is less than 260 days. So, what do I want to do?
Normal CDF.
Normal CDF. Can I finish my picture first though?
Oh, sure.
What would my picture look like?
Highlighted from the left down.
To the left of
So, I'm trying at 260.
260. So we have to find the 260, which is roughly here. And everything down, Hector says. We agree it's going down to the left
Yeah.
because
This is less than.
less than. So now Brian says we want to do normal CDF to find that probability. What am I going to put into my calculator?
Negative 999.
The number on the left here is negative 9999. The number on the right is 260. My mean was 268. And my standard deviation was 15. What do we get?
2969.
2969? The follow-up question asks if it's unusual. Change that to unlikely. Is it unlikely for a woman to have a pregnancy that lasts less than 260 days?
No.
It's not unlikely for that to happen, because it happens roughly 30% of the time. It's not very unusual for one woman to have a pregnancy that's that short. Okay with that part? Let's really review what we did. Look at the subtle difference in part B. So now you have 25 women who went on a diet, and it says find the probability that 25 selected women have a mean pregnancy length that's less than 260. What? The mean is less than 260. The average of those 25 women is less than 260. So highlight or underline that word mean for sure, because that's the big key here.
You use that formula?
That's that formula I was just talking about, yeah.
Whoa.
So in this case, if we wanted to write out the question, this was the probability that one woman had a length less than 260 for an X, right? Agree that was the question that we just did over here? Over here, what are they asking?
For the mean.
The mean is less than 260. The word mean is crucial in that one. So there's two parts to tell you something's different. They're talking about the probability of the mean, and they're telling you they have a group of 25 people. Over here, they just talked about one woman, right? Now they have a group of 25 women. They're giving me an N, a sample size of 25 women. So the two keys are they're asking about the mean and they're giving you an N. When that happens, you have to get the new standard deviation. Other than that, it's the same question. It's much less likely when you take a group. So we have to do the new standard deviation. We take the old standard deviation divided by the square root of n, which in this case, the old standard deviation was, what was it? 15? Divided by the square root of 25. The new standard deviation is 3. What? Which means the averages won't be as far away from what we expected. Just like the guy who makes $200, right? One guy who makes $200, that could happen, but to have the average be that much is just really extreme. So it changes how spread out your numbers are. My picture now looks different. 268 still goes in the middle. But what am I going to count by now? Count by threes. These are now X bars, the mean. I'm going to count by threes now. I can do that easier. 271, 274, 277. I'm adding and subtracting 3. So the key that tells you need to use what's called the Central Limit Theorem is the key that it said their mean is less than 260 and they gave you a sample size. What does my picture look like now? Where's 260? Yeah, way over here now, right? 260 has now moved. And less than 260 is this little tiny tail over here. To the left of 260. Do you agree that just the picture alone, that has a much smaller probability than this one does? How would I find that probability? Normal CDF. Almost the same thing I did right here, except that
It's the opposite. The upper number is negative.
it's still the same region. I'm still going from over here to there.
Just change the standard deviation.
Aha, all I'm doing is changing the standard deviation, right? I'm still going from negative 999 to 260. I still have the same mean. The only thing that's different is my standard deviation. I'm going to write it up higher just because it's going to be too low for some of you in the back there. So it's normal CDF, negative 9999, 260, 268, and 3. This is the only thing that's different. There's a 10-point problem on the next exam where I ask you this question almost identically. I mean, it'll be a different situation. But it's just making sure that you recognize that you need to use that new standard deviation. What's the answer here?
0038.
0038? That's a very tiny probability. It's really unlikely for a group of 25 women to have an average that low. It's not unlikely for one woman. We talked about that over here. One woman, it's not surprising. Happens 30% of the time. But to have an average that low, extremely unlikely. This is really unlikely to happen. So look at the question there. Part C. If 25 women do have a mean less than 260, so something's really unlikely, but then it happens, does it appear that the diet had an effect? These 25 women all went on the same diet, and then they all had an average pregnancy less than 260, something that we know is unlikely to happen. What would you say? I got a couple people nodding. Let me word it again. If 25 women go on a diet that doesn't affect them, the chances that their pregnancy lasts less than 260 days on average is 0.0038. Extremely unlikely, almost zero. It's almost impossible to have a group of 25 women have a pregnancy that's that short on average. So if their diet didn't affect them, it's almost impossible to happen. But it did happen. So what do we think? The diet must have affected them. We don't know for sure that it did. That's going to be some more research, obviously. But that's the whole point of statistics. We assume that the diet doesn't affect them. And then we say, well, how likely is this to happen? Extremely unlikely. Oh, then maybe our assumption was wrong. Kind of going back to, I don't remember how long ago it was now. If I assume I have a fair coin, but I flip it 100 times and get 99 tails, we're not going to assume it's fair anymore. Because that's so unlikely to happen. So we're going to assume that these women are all fine on this diet, but something happened to them that was so unlikely that we're thinking that maybe the diet did have an effect on them. So the answer to part C is, yes, it appears that it has an effect and the medical supervisor should be concerned. Something happened that we know statistically was really unlikely to happen. What if one woman has a pregnancy less than 260? Are we worried? If one woman does? No, that's 30% chance that could happen just randomly, right? It's no big deal. 30% of the time that happens for one woman. But as soon as you had that group that had an average, now we're concerned because it's so unlikely to happen for the group. Okay, let's do one more of this. Now we're going schemes. Page 80, last example here. And in the interest of time, I'm going to skip example A and just do B. Let's talk about the difference in them and why I can skip A. Read question A and question B. I'll give you a minute to read the top and read those two. Page 80.
Is it working with the same numbers?
I couldn't hear you say.
Is it because we're finding the greater, the weight greater than 167 in both of them?
So they're both doing a greater than 167. Both part A and part B are asking the same question. But what's the other difference in part A and part B? B is talking about the mean. See how part B says that the 12 men will have a mean greater than 167? So it's similar to what we just did with these pregnancies. We could talk about one woman, but what about the group of 12 or 15 women or 25 women we had over here? Sorry. So in part A of this problem, which I'm going to skip because we're going to run out of time if I don't, do I need a new standard deviation
Yes.
in part A?
No.
Part A I don't, right? Because it's just one man.
B.
But part B, we will need a new standard deviation. And what are the two key things in that problem that tell me I need a new standard deviation?
The mean.
The word mean
12 remnants.
and the 12 men, exactly. The fact that I have 12 men and they're talking about a mean. And I'm going to do this one without even drawing the whole picture. See if we can handle that. Watch me live on the edge in the last 3 minutes. What's the mean?
172.
172. Men's have weights, it's up at the top there. Men's have weights of 172 and standard deviations of 29. But in this particular case, because I'm doing X bar, my new standard deviation is going to be
29 over 12 square root.
29 over square root of 12. The sigma over the square root of n? Not a nice number like last time. Someone help me out, give me a decimal.
8.372.
8.372? I'll say 8.37. Someone agree with Ariana?
Yes.
Okay, so I have that. I have my 172. The question is, what's the probability that these 12 men will have a mean greater than 167? 167 is over here somewhere. To the left of 172, right? I'm not labeling the whole thing, I'm just gonna get an idea. Just finding where 167 is. Greater than means what? To the right. I want to find that probability. So what am I going to do?
Find the less than and then subtract it from there.
Actually, with our calculator, we just have to tell it the number on the left and the number on the right.
Oh, okay.
You could do that, but we don't need
Or
to.
it'd be 167.
167's on the left,
9999.
some really big positive number on the right.
And then,
The mean, which was 172. And watch what I'm going to type in right here. When you go to do this in your homework, you can actually type it in just like we have it written up there. You don't have to first find it and then put it in there. You can type it in exactly like this if you want. 29 divided by square root of 12. You could put in 8.37 if you want, but that got rounded. You can type it in just like this. 0.5,
6, 8.
5, 6, 8. So I know we're out of time, but the question was, this is how the gondola would be over its maximum weight. So there's about a 57% chance it's overweight. You want to get on?
No way.
No way. Yes. So what'd you put? Different answer? Uh-oh.
I did.
Uh-oh, you just got outvoted. I don't know who got me the 5, 6, 8. What's the other answer?
7, 2, 4, 2.
I got two.
Someone tell me, starting from beginning. Point.
7, 2, 4, 8.
7, 2, 4, 8.
That's what I got.
Uh-oh. 7, 2, 4, 9. Is that what you got, Christiana? It's either 4, 8 or 4, 9 based on whether or not you rounded here. I'm not worried about that. If you did this one or this one, you'll get a slightly different answer. It's either 8 or 9, depending on if you did this or you did that. Either way, it's more than 50, now it's a 72% chance it's overloaded. I don't want to get on. They should do something about it. I'll see you guys next time. If you didn't get this number, let me know. I don't remember who gave me the first one. Brian, was that you?